Can you see my screen share?
Yes, sir.
Okay. Yes, so we are reading cathode ray oscilloscope. So yesterday, so all the construction detail and the functionality, everything we discussed, and we discuss how a input signal can be displayed in cathode ray screen, CRO screen, and also we discuss that how from the screen we can take the measurement using scale, and also we discuss that how voltage can be measured, how frequency can be measured, how time period can be measured, and we are discussing how phase difference can be measured. So in CRO, we have said that this is the panel and there is a scope of giving two signals through the uh, two scope because there are two channels are there. You can see the channel 1, you can see the channel 2, and you can see the number 9 point on the left hand side where it is the point where you can attach the probe. Similarly, right hand side corner below there is a similar circle you can see, so that means that another probe you can attach with it, and that probe has the two points or two place where you can attach the probe to the wires or somewhere. So you can give two input signal, and you can give two input signals and you can see the display of the waveform in the two input signals. Okay, so you can measure the two signals at a time, so you can measure everything, two signals, amplitude, voltage, and everything. So another interesting thing you can measure using the CRO, that is the phase difference. So for that you need to apply the two signals in the two channels, and from there you can determine the difference of phase. So for that you need to press XY. You can see the XY button here. So you can press the XY button. So you have to give the two signals in two channels. Suppose two sinusoidals you are giving, and if you press XY button, you will see you can determine the phase difference between them. So how you can do it? For that, if you press XY, what will happen? The two channels input will be superimposed. So they will form a Lissajous figure. So what is Lissajous figure? So when XY we press, then one vertical and horizontal, there are two um, plates. So in one plate, one signal, input signal will come. In another plate, another input signal will be provided. And when both the signals will be given to both the plates, then the resultant waveform will be the summation of these two, not summation, the resultant waveform will be the waveform will be displayed on cathode ray screen, and that from that display you can determine the phase. Now the question is how. So here if you see that if the phase, there is no phase difference, what will happen? Both the uh, signals will form a linear line along the uh, kind of diagonal, and that is the phase is zero. Now suppose in horizontal plate we gave a signal which is same signal, and vertical plate we gave another signal which is 30-degree apart. So you will say that the a slant is ellipse kind of thing whose axis will be on the first quadrant and third quadrant. Okay, now if it is more, say 60-degree, so the ellipse will be little bit uh, kind of flattened, or near to circle it will come, but the axis will be still on the first quadrant and third quadrant. Now if the angle becomes 90-degree, you will get a circle Now, if angle becomes 120 degree, what we will get? You will get an ellipse whose axis will be on second quadrant and fourth quadrant. And if it is 150 degree, you will get the ellipse of thin ellipse, okay, whose axis will be on the second quadrant and fourth quadrant. Now, if you give 180 degree, it will become again a line whose axis will be on the second quadrant and fourth quadrant. So these are the typical values of the phase difference, and the figure shows that how the Lissajous pattern will look like. So it is clear that whatever be the based on the phase difference, you will get a kind of ellipse whose axis might be on the first quadrant and third quadrant, or the axis might be on the second quadrant and fourth quadrant, major axis. Sorry, I should say the major axis. So now using the cursor and the scale which was drawn on the cathode ray screen, CRO screen, from there, you can know the length of, say, for figure A, you can know length of, say, y2. You can know the length of, say, y1. You can know the length of x1. You can know the length of x2. That means you can know the y length where the maximum ellipse, maximum points is there, and you can know where this axis is going to cut. And similarly, on the different slanted ellipse, you can also know the y1, y2, x1, x2. Now, from this measurement, oh, it is not written. So, from this measurement, what you can do, suppose you see that the figure on A, okay, you see the figure on A. So, in this measurement, you can know that x1, x2, y1, y2. Suppose you know the y1, y2. Then, how do you determine the phase? So, determination of phase, now let's see a simple one, this one. So, suppose you have ellipse, and from this, we come to know that what will be the A length and what will be the B length. Then the angle will be the sine inverse A by B. So simply you take the value of A and B and you give the angle. So angle will be sine inverse A by B. So this way from the Lissajous figure, you can also determine the phase angle between two input signals which are provided in channel 1 and channel 2. Now tell me if you have query at this point. So basically what we did, we finished the CRO. So it takes a lot of time. So 2 classes it takes, but still we consider the CRO in every detail. We consider construction, we consider, and what we can measure, what we cannot measure, everything we consider. So now tell me if you have any query on CRO. Okay, so as you people are not asking any question, so we can move the next topic. So next topic is storage oscilloscope. Okay. So what do you mean by the storage oscilloscope? So there are two types of storage oscilloscope: analog storage oscilloscope and digital storage oscilloscope. Okay. So whatever the CRO we discussed, that is not. So whatever the CRO we discussed, that we can see the displayed signal or the signal attached. You can take the photo also, that is not an issue, but the measurement system itself is not capable to capture, okay, or to store the data. For example, what I was saying is, with this CRO, is it possible to see at the later point of time with what time, what value of the voltage was? No. Okay, you cannot store. You cannot store the time versus this amplitude of the voltage. You cannot store. So there is no option of storing. So CRO is not a storage oscilloscope. So there is another type of oscilloscope which is little costlier, where you can store the data. So those oscilloscope are called the storage oscilloscope. Now DSO, digital storage oscilloscope, is very popular. What I was saying that in class in lab 101, all of you are using that because you people like that. So that instrument not only can display, it can also store the waveform values with the time. So how it can do it? So let's try to see this block diagram. So in this block diagram, you see CRT is there, cathode ray tube is there, okay, and in cathode the uh, apart from that, there is a separate, there is more circuits, okay, in the storage oscilloscope. Now let's see what is the circuit. So whatever input signal you give, there is a buffer amplifier, okay, and sample and hold circuit. That means what it is doing? It is sampling and holding, and then ADC. ADC means analog to digital converter. So whatever signal you are giving, that is being converted to a digital signal. And you see once it is converted, so if you have an analog signal, you have to convert it in digital signal, then only you can memorize. How you can memorize? You means your instrument. How you can do it? Suppose you have some signal and then you want to know the values at some point of time, say 0.1 second, 0.2 second, 0.3 second, or you can know 0.01 second, 0.02 second, 0.03 second, and so on. So you have to sample at that interval. And without sample, how do you know? And it is not possible to know continuously, because how do you know the continuous signal? Continuous signal, you cannot store time versus this. You have to have some waveform. Uh, you have to have some waveform expression. Then only you will see the continuous signal. But here you are memory. Your instrument is keeping the memory of the time versus the signal amplitude voltage. So you have to sample it. So you have to do analog to digital converter, and at some sampling frequency, which is at some interval of time. So it knows what the value of voltage is, that is A to B sample and hold circuit. So it samples at some point, samples and hold the value of voltage, and those things went to memory. So storage. So this memory or storage, due to that, it is called the storage oscilloscope. Okay. Now, if you come to this, there is another control circuit. Okay, what is that? You see, clock sample is we are giving, and we are having the external trigger and internal trigger. Suppose our signal is at internal trigger, and we are giving a clock sample. So at the when the clock rises, what does? Here is a address counter. Okay, so in the memory you have to have address. So in that address it will be stored. So when the clock rises at that point, it gives the input to sample and hold circuit, it gives the input to ADC, and then it gives to the address counter. And when at the rise of the clock, see, address is activated, and then you sample at that point of time, and you get the, your voltage values will be in the memory with the address counter. So sample is required. So suppose in clock sample, we increase the clock sample or the frequency or the time period, we decrease. So then there will be the sampling time will be increased. If clock is very fast, then sampling time will decrease. You will get more numbers, okay, very quick storage or very quick samples. So this is all about the storage. So due to this thing, we call it a storage oscilloscope. Okay. Now, when the uh, when the data are stored, then the display come into picture. Okay. For display, what we do, from memory we take the data, which is called the DAC. So digital to analog converter. Again, because in memory it is in the digital form, discrete form. So digital to analog converter, it is simply it is digital to analog converter, and then the input signal becomes second analog. This analog signal will go to vertical amplifier, and then from the control circuit you see that time based counter is there, DAC is there, digital to analog converter again, and it goes to horizontal amplifier, and cathode ray tube shows the output. So in storage oscilloscope you can see the output, you can store the output. Okay, and here the transient can be captured because you see that you can store whatever you time you can store, and that cannot be displayed, but still you can store and get the data. Otherwise, when the waveform is sinusoidal or square or sawtooth or triangle, you can store it and you can then see it. So in the DSO there is some option. Option means user button is there, where whatever you are seeing or it is displaying, you can store it in the form of time versus voltage, and that storage data can be taken out from the DSO using the USB storage or other storage device, and you can see or plot in the computer. So this is all about the storage oscilloscope. Now you tell me. So if you understand, we will move to next. There is some question. Let's see. Okay, no question. So then move to the next. Electronic instrument. So here we'll read a few instruments which you use day-to-day life in your labs. So if you see the digital multimeter, yeah, the most popular instrument you use in lab. So everybody wants digital multimeter so that you can measure voltage very quickly, resistance also. So now you see in digital multimeters, there is some input. Left hand side, you can see there is a point where it is written input, and there is a current source you see. So that input you see is going to, one point is going to buffer amplifier, and then there is other DC voltage which is going to calibrate it or attenuate it, and there is DC current, AC voltage. So you can measure all those things. So input can be whatever I'm saying. Input can be resistance, input can be DC voltage, input can be AC current, input can be DC current, input can be AC voltage. So with multimeter, what are the different things you can measure? In multimeter, you can measure the input. Your input can be, you can measure resistance, you can measure the DC voltage and current, you can measure the AC voltage and current. You have to be very cautious. Most of the students, when they want to measure the current with the uh, digital multimeter, they used to keep the multimeter on parallel. So the parallel, it cannot be. When you attach this multimeter in parallel, it can only give the either the resistance or the voltage. So to measure the current, you have to make it in series in the circuit. Then only you will get the current. Otherwise, you will not. So that you have to be very cautious. So for measuring the voltage, you have to give it on the parallel. To measuring the current, you have to make it in the series so that whole current pass through the digital multimeter. Same principle of ammeter. So now you see the input can be resistance, input can be DC voltage, input can be DC current, input can be AC current, input can be AC voltage. When there is a DC voltage, suppose we want to measure the DC voltage, and also in multimeter, you see there are the different range. So suppose 0 to 1 volt, 1 to 10 volt, 10 to 100 volt, 100 to 1000 volt, like that. So whatever is your tentative input, you feel you have to keep the first thing is you have to keep your pointer. Pointer means that movable thing, either AC or DC, and in AC or in ohm resistance, or if it is AC voltage or current, if it is DC voltage or current. So there also, if you want to measure the voltage, with AC voltage, you have to keep that movable pointer, movable pointer on the pointer, that movable plate on the mark where the AC is written, and from there AC voltage, and then you have to keep that thing uh, at the proper place. Proper place means whatever the tentative voltage. Say you want to measure from 0 to 1 volt, so you keep on the 1 volt range. You measure 1 to 10 volt, you keep on the 10 volt range, like that. So once that is done, then you attach your multimeter, either in series or in parallel. Suppose you want to measure the DC voltage, then you apply your multimeter in the parallel. So what will happen then? Inside the multimeter there is calibrated attenuator. Attenuator is there. So whenever you are changing the range, the attenuator is going to change, and from there it is going to A to D ADC converter. So this analog voltage is converted to digital, and from there, if you want to know the values, so this digital thing is processed with the electronic circuit. For example, if you want to know the frequency, that will be processed with a clock and the counter. If you want to know the voltage, then that could be processed with the, once A to D is converted, then you can see and measure the time period, and then from time period what is the peak or RMSE, you can tell. RMSE you can determine. Similarly, DC current also shunt will be there, because not all the current will pass through it. Small amount of current will pass through it. So rest of the current will not pass through it. So for that shunt is required, and shunt is built inside with the range. So after the shunt, again it will be A to D ADC, okay, analog to digital converter. Then again AC current, there will be a shunt, and AC voltage, there is a calibrated attenuator. For AC thing, you will see that precision AC to DC converter is there. Okay, so for AC thing, AC to DC converter. So once it is converted to DC, then again it is converted to analog to digital converter, and from there you can see, you can calculate the peak voltage or RMSE whatever, and you can display it. Now, when it is a ohm, then there is a current source, and then IV method, resistance is determined, and there is buffer amplifier. Again, that is converted to A to D ADC, and then that is displayed. Okay, so this is the full thing about the digital multimeter, which is very popular among the students and everybody, and it is very cheap also. So with the help of digital multimeter, you can measure DC voltage, AC voltage, DC current, and ohm. So whenever you are measuring the DC voltage, you need to have attenuator and then ADC, then it will be displayed. When you are measuring the DC current, you have to have shunt and then ADC, then it will be displayed. When you want to measure the AC current, then again shunt. Whenever you want to measure the current, you have to have shunt. Whenever you want to measure the voltage, you have to have attenuator, because for measuring the current, you need to connect it on the series and not whole current to pass through it. So you need to have shunt definitely. And when you want to measure the voltage, you have to keep it on parallel, and then very small amount of current will pass. So that's what you need, a huge resistance, which is called the calibrated attenuator. And for AC measurement, always you have to have AC to DC converter. So once you convert in AC to DC, then analog to digital converter, ADC, then you can display. So generally, when previous days, like 4 or 5 years back, in control instrumentation lab, I used to give small project. For example, you design a circuit so that you can measure the frequency, or you design a circuit so that you can measure the voltage. You design a circuit so that you can measure the current, like that. But then I see that the students are not taking any interest at all. Okay, so then this gradually and slowly, this concept of small project in lab, it is not there. So last few years, there is no project. The student comes, do the labs, and they give the exam. So all depends on student interest. So students are not taking interest particularly on electrical related stuff. Okay. Okay, fine. Now tell me that if you have any query. Okay, so you are not asking anything. Let's start. So in digital multimeter, So I said that whenever you want to measure current, you have to need to current to voltage converter, then A to D ADC. So how you can convert the current to voltage? It is very simple. You have read op amp in your analog electronics course. So with the op amp, if you give connect this resistance on the uh, minus uh, point, that means if you give this resistance as a negative feedback, okay, then some input, if you give input current, what will happen? You will get some output based on the resistance. Okay, so if you give some input current in, so it will go through IR through the resistance, and you will get the ADC of DMM. Okay, digital multimeter, it will go to the A to D converter to digital multimeter. So ultimately this diagram, what it does, it with the help of ammeter we can convert a current to voltage. So if some current you give IN, so based on this feedback resistance, you can, the output of the amplifier will be a voltage, and that will go to A to ADC. Okay, this is all about the multimeter. Then there is another instrument which is called the frequency counter. Frequency counter instrument, what it does, it shows the frequency. So in multimeter, you cannot see the frequency because it is not designed for so. So frequency counter, there is another instrument which is called frequency counter. With the help of that instrument, you can count the frequency. This also another uh, our previous labs one of the projects, okay, design frequency counters. And earlier days, student used to take lot of interest in doing these small projects related to electrical engineering. Now somehow the all the students don't want to do anything, don't want to do BTP, don't want to do design lab. I don't know what students want to do. So now let's see that the frequency counter, you have a input signal process. You see that input signal, and there is a block. You see this input signal processor, and you see there is a gate, and you have a time base. Okay, so input signal is coming, and with the time base you make an AND gate. So what will happen? Suppose our time base is t plus delta t. So at the time of delta t, up to the time of delta t, we take the input signal. Now whatever the input signal comes at the time of delta t, then we will convert that input signal to a square wave. That we can easily do with the help of a comparator circuit with the using op amp. So with op amp we can make a comparator circuit, and with the comparator circuit, what you do, you make this input signal as a square wave, and this square wave then you have a make a counter. So with the help of counter, you just count the uh, number of latch, I mean when the square wave is going to small to high, and that count will be proportional to the time of the base signal. And then you know the time base, you know the count. From these two, you calculate the frequency. It is not very difficult, right? So, and that is stored in memory, and that can be displayed. So in memory, you see that time base is also going, count values is also going, and from there it is possible to determine the frequency with some arithmetic operation, and that can be displayed on the screen. So this is all about the frequency counter. Basically, when you have some sinusoid or some square or something, you bring the frequency counter, you give the input circuit, what will happen? You will see the frequency of the signal. How you can see? I'm repeating once more. So what you can see? So the input signal is taken. You have, there is one time base, and in the time base, the input signal is taken, and then input signal can be converted to square wave, and then the square wave can be count. Count means that when the square wave goes from zero to high, so that latch going out, that can be counted, how many times it is going zero to high. And from that count and the time base, both goes to memory. In the memory, there is some arithmetic operation with the count and the time base. It is very easy to determine the frequency. And then once the frequency is determined, it can be stored or it cannot be stored based on the instrument, but it is displayed. Okay, So you see the frequency in the displacement, in the display. In the digital display, you see the frequency. That is the frequency counter. Yeah, here it is more, it is given. So input is say like this because the input signal we make it to square wave. And then if you see that when we make the input signal as a square wave, we have a gate. So through the, at the time of gate, the square will remain the square wave, other time it will be zero. So you now you apply a counter to measure the how many times this low to high transition is happening, and that counter and the value of the window of the time through which this get applied, you divide these two, you will get the frequency. Okay, that is very simple. Student used to do all those things in lab by their own electronics and own thinking, so they learn a lot. So when you do some work in practically, you will see that how whatever I say that loading effect you will not realize, but once you do one single project on your hand, you will realize that what is the meaning of loading effect. Okay. Okay, but if you need, so all the resources, everything is there. So but you need to have students attitude to do something. Now there is another instrument which is called the frequency selective wave analyzer. So this instrument is also available in the market to buy. So let's read the heading: frequency selective wave analyzer. Okay, basically it is a wave analyzer. What is wave analyzer? Suppose you want to, I ask you a few questions that suppose you have a time domain signal, A sine omega t, sinusoidal signal. Which domain I am describing? Time domain. How it can be described in a frequency domain? None of you answer it. But it is I give the hints that signal and system. Did you read? All of you say that yes, I did. So then you please tell me that how a time domain signal can be represented in frequency domain. But only one student can answer, I guess. So none of the student answer. But I don't know what you read in signal and system. So it is very simple. Suppose you have a frequency domain. Suppose you have a time domain signal. You want to represent it on the frequency domain. What you do? You do the Fourier analysis. So in Fourier, what is the output? In the time domain, the graph is time versus voltage. In the Fourier frequency domain, the graph is frequency versus the voltage. Okay. So, so the main concept behind this, again, I am repeating, although you read lot of more things in science, systems and signal course, still I am repeating once more that when you want to, when you have a time domain signal, it is, it can be shown that any time domain signal is a sum of many sinusoidal waves. Okay, so suppose you have a signal in the time domain, which is say the triangular wave, which is a periodic and which is varying with time with some period, and that can be represented as a sum of many sinusoidal waves. Okay, and so when you say the sinusoidal waves, you have a frequency and you have amplitude. So you have many frequencies and many amplitude. So when you plot those frequencies and amplitude, that becomes a frequency domain representation. Okay, is that clear? And frequency selective wave analyzer, it does the frequency domain representation, or it shows the signal in a frequency domain when you give a signal of time domain applied to this instrument. So when I was saying, suppose I was saying that you want to see the signal in the time domain, you have a cathode ray oscilloscope. Now frequency domain, how you can see? Either you take the time domain signal, you do the Fourier analysis and then Fourier transform, and then you see that what are the frequency domain signals are coming. Or there is an instrument which is readily available. When you plug it the signal to when you plug it the signal, then output will be frequency versus amplitude. That means frequency domain representation. Tell me, this is the basic, whether you understand it or not, or you have any query, or you want I to repeat it. Whatever you like, you tell me. There are very small number of students. I don't know what the rest of the students will do. They always feel that this hearing the voice which is recorded is sufficient. It is not. Okay, fine. So, do you understand that what is frequency domain representation. Okay, let me proceed. So suppose you have a time domain signal, and when you want to represent it in the frequency domain, what you have to do? You have to do the Fourier transform. So now, if you have a not continuous time domain signal, say you have a time domain signal data, which is sampled at some interval. So you have a data time versus the amplitude data in time domain. When you want to convert this data in frequency domain, you need to do the discrete Fourier transform. Okay, this. So this discrete Fourier transform, sometimes it is algorithm. It is an algorithm. Sometimes it becomes very tedious to do. Then you do the first Fourier transform, which is called the FFT, which is very popular among us, and maybe you mostly know this term FFT, fast Fourier transform. So this is the main philosophy, that if you have signal in time domain, it must be represented in frequency domain. This is very important representation, because in you can see that how many harmonics are present and what will be the amplitude. Based on that, you can process it, and after you say amplify it, what are the different distortion, what are the bandwidth of the amplifier required, everything you can determine based on this. So you need to know the frequency domain representation. So when you do the frequency domain representation from a time domain representation, you can do it either by knowing the time domain signal or the values, discrete values, and then doing either Fourier transform or fast Fourier transform. Or we have an instrument readily available in market which you can buy, and the input signal you can plug in. As an output, you will see the frequency spectrum, which means frequency versus amplitude. Okay, so all the frequency means the sinusoidal frequencies, and amplitude means amplitude of that. So in mathematical, if you write all the frequency summation with that amplitude, so a1 sine omega 1 t plus a2 sine omega 1 omega 2 t, like this, ultimately you will get the time domain signal. Okay, super input of all these. Okay. Now, if you see how this instrument, what are the different blocks of the instrument? So first we have the input, signal input, which is coming, and you have the input attenuator. Now, then it is the important block is the variable frequency high Q active filter. Okay. So you filter it. Hmm. Variable frequency, you know that up to which frequency you can filter it. So input, I am assuming that you are giving any arbitrary input signal, and that might consist of frequencies which ranging from very low to very high, infinite, and it may not be always possible. So frequency selective. But if you want to see that within a frequency range, say 1 radian per second to 1000 radian per second, how many harmonic components are there? Then you have to select that frequency range. That's what the term frequency selective is coming. So this block is for frequency selective. So variable frequency, that means you can select the frequency, and frequency selective means you have to select the filter of that frequency, and it is a high Q active filter. So here you must have an active filter with high Q, and from which you can select a variable frequency band, and ultimately will display the voltage versus frequency in this frequency band. Okay, then it goes to that output amplifier, and in output amplifier to it goes to the meters and detectors, and you see their output meters, and also it goes to the sometimes recording device so that you can record it. And ultimately what you will see, you will display that the different frequency versus amplitude. So and you will see that the or in record you can, it can record the frequency versus amplitude. Okay, so basically the main things is required that you need to have the frequency filter, and once it is a frequency filter, you have the you have the signal, then you can take this signal, you can do the FFT, and then output amplifier, and then it goes to the meter, and also it can go to the recording device so that it can record it. So this is called the frequency selective wave analyzer. You read all those things from Kalsi. There it is given very detailed. Okay, Kalsi is the book which I refer. Uh, so most of the instrument is also available in Sahani, but Kalsi book, these type of things like the DSO, then frequency selective wave analyzer, then frequency counter. It is there in great detail. You can read it. Now digital voltmeter. How what is that? So digital voltmeter is also a very simple instrument. You have a gate, two gates basically. One is AND gate, and you have a width of T, and in that width you will get the input pulse. And once, so it is a pulse generator is there. So input voltage, based on the input voltage, the pulse will be generated, and there is another continuous pulse. It is coming, and based on that you have a AND gate, and you will get for that period of time you will get the pulse, and then you have a NOT gate, you just invert it, and then you count it, and after the counter you represent the counter, display the counter up to some decimal place, and after that it is reset, and then again you can do. So that count is, will be proportional to the voltage. Okay, because input voltage whatever is given, so you are taking the pulse generator, and based on that input voltage, the pulse width will depend. So if input voltage is high, the pulse width will be high. If input voltage is low, the pulse width will be low. If the pulse width will be high, there will be more and more, there will be more the spikes, and the counter will be more, and then counter value can be calibrated with the input voltage. Okay, so input voltage, we have attenuator, we have a ADC, we have a counter, we read out device. So again, I am saying if you miss something, so if you have input voltage, you have a pulse generator. Pulse generator means based on the input voltage, your pulse will be generated. If input voltage is high, your pulse width will be high. If input voltage is low, your pulse width will be low. Just wait 1 minute, I am coming. So your input voltage is high, so then pulse width will be more, and you have a spikes, and then for that you count the spike. If the pulse width is more, there will be more spike, and you counter value will be more. You display the counter value, which is same as the voltage. So you, if your input voltage is more, your counter value is more, you display more. So you can calibrate the display with the input voltage. Okay, this is all about digital voltmeter. Okay, so now you tell me. So you don't have any query, that is fine. But you see that we have covered many things till now, and almost all the electrical measurements. It is not possible to cover every electrical measurement, but we have covered almost important electrical measurements. For example, we have, so initially we start with the philosophy of philosophy of our measurement system and different characteristics, and how the measurement system dynamics will helpful, or all those things. And then we directly go to the electrical measurement. So in electrical measurement we read the meter. For example, we read different PMMC, moving iron, electrodynamometer. Then we read the bridge circuits. Okay, then with the bridge circuit, how you can measure, you can measure the inductance, how you can measure the resistance, how you can measure the capacitance. Then from after the bridge circuit, where we move the measurement of resistance. We read how you can measure the high resistance, how you can measure the low resistance, how you can measure the medium resistance. After that, we go to the electronics measurements. There, how we can display in CRO, and there are many other electronic measurement. For example, multimeter, DSO, digital storage oscilloscope. You measure the digital storage oscilloscope, DSO, and then again we read about the measurement of voltage, measurement of frequency, measurement of frequency selective wave analyzer, and whatever the instrument we use in day-to-day life, almost everything, electronics instrument and electrical instrument we have discussed. Okay, so now you can see that the part A of this electronic instrumentation syllabus is complete. So there is another part which is part B that we are going to start. So let's take 5 minute break. Then we will start part B. So in part B, what we will read? We'll read the measurement of different physical variables other than electrical. For example, if you want to measure displacement, how we will measure? If you want to measure the velocity, if you want to measure the acceleration, if you want to measure the displacement, how do you measure? If you want to measure the strain, how do you measure? If you want to measure flow, if you want to measure the pressure, if you want to measure the temperature, how do you measure? So those quantities are non-electrical quantities. So those parameters are non-electrical quantities. So that is what it is a part B. So in part A, what we do, we read about the philosophy of the measurement system and the electrical plus electronics measurement. Okay. And in part B, we will move to the measurement system which is non-electrical and non-electronics type. For example, whatever I said, these physical parameters, temperature, pressure, displacement, velocity, okay, all those things. So how we can, okay, acceleration, vibration, flow, temperature, all those things. So that will go to the part B, and that part B now will start after 5 minutes break. And in part A, I said that what is the book you should follow. Every section I said the book. Part B, the mostly you must follow the Doeblin. That is a very, very good book. And you can read the Doeblin line by line. Very good book. You will understand everything. I will also teach from the Doeblin. I will take the figures from the Doeblin. I will take the explanation from the Doeblin. So if you read Doeblin, it is more than sufficient. Okay. So once we complete the part B, your syllabus will be completed. Okay. Now please take a 5 minutes break.